Okay, guys, today I will show you how to extract monthly rainfall data from CMIP6. So we know sometimes we download CMIP6 monthly rainfall data, but in the form of .NET-CDF file. So by using R, we can extract this data by using R for monthly rainfall. So recently I'm working on monthly rainfall for uncertainty assessment of CMIP6 data. So I have download 28 GCM from CMIP6 data. So today I will show you how I'm extracting that data and put it into Excel file based on the grid location for Peninsula Malaysia. So let's share the screen, entire screen. Okay, let's put myself down there. Okay, now this is the R code that I have prepared for CMIP6 extraction for monthly rainfall. So I put it code repeat because this code is you use for extract each of the GCM. So the GCM that I have downloaded is 28. So I can show you here. Where is it? Did I put here? Monthly historical. No, it should be here. Access, I see ensure. Yeah, GCM. This I have 28 GCM monthly rainfall for historical, and the condition is 100 kilometer monthly rainfall with 100 kilometer nominal resolution. It has historical and SSP 5. So I end up with 28 GCM. So all the GCM is in the form of .NET-CDF file. You see all the .NET-CDF file. This is .NET-CDF file also. All the GCM is .NET-CDF file. This CSV is the data that I have extracted by using the code that I have here now. So all the data is in the .NET-CDF file. Some of the GCM have many parts. Some of it have very smaller part. So we want to extract this GCM and in the form of .NET-CDF and extract for certain part of our study area. So all the GCM is actually global. You need to extract it. Where you want to extract it, you must decide. So after you extract it, you will get this result. Let me close other. You have like 150 until 2014. 2014 here result. So this is for Peninsula Malaysia. So I have download this extract this GCM 178 grid point. So for monthly rainfall. So I will show you how I did this one by using this R. So first you must install the library RGDAL. Let me make it bigger. Okay, RGDAL. If you don't have, cannot see all the writing up here, please use increase your resolution of YouTube. So and then you need to install the package NCDF4, and then library for raster, and then YA impute, and then library for SP. So and then do this memory limit. I think it's no longer supported here. It said something like that. So yeah, just whatever. It doesn't affect anything. So and then you find where you put your grid file, where you want to extract the data, which grid you want to extract. So I have Peninsula Malaysia grid 178 grid point. So I put it in this folder, working directory. I see ensure 2024 just now. So PM grid Peninsula Malaysia grid point. So put your grid point like this. You have let, long, and then grid. Number 1 until 178. So I want to extract the CMIP6 data just now for all these grid point. So this grid point is 0.25 for chips data rainfall data. So I want to extract it for each chips rainfall data location in Peninsula Malaysia. So this is where I want to extract the GCM, because GCM is the global data. It's up to you which part of the globe you want to extract it. So I want to extract for CMIP6 data in chips based on the chips data in Peninsula Malaysia. So GCM actually they have different resolution, 100 kilometer in this case, because my constraint of CMIP6 data when I'm download it is 100 kilometer. So each GCM have different resolution, but I want to make it homogeneous by using bilinear interpolation. I will interpolate it when we extract it. We also interpolate it into this chips rainfall data so that we can make a fair comparison between all the GCM that I use later on when we want to find the top performance GCM. So we want to do something like that. That is how usually people do a comparison. You cannot compare one GCM another GCM with different grid point. It's not possible to do that one. At least the justification why we do interpolation is to the grid point of the historical data. For in this case, it's historical data is chips data set. We want to compare it with the historical data so that all these GSM will have the same resolution, so that it can comparable, apple to apple, something like that. So we set working directory just now. We read the let long for Peninsula Malaysia, and then post we get 1 and 2. This is let long, and then we read the observe read PM grid, and then do raster from XYZ. Okay, XYZ, and then set working directory. For example, for this one, I want to extract Thai ESM2. So you can read my data just now. I want to extract Thai GSM2. So I will Thai this CMIP6. I read this file. So this file, it will read the file and then extract data. Now we extract the data by using this code. So when we run this code, for example here, when we run this code, this for me, and then pre, and then we do the brick, and then if we run pre, I think pre, oh no, no need to run that one first, and then this is the method for interpolation that we use. Bilinear is usually people use for interpolation because it's one of the best method to interpolate rainfall data or temperature data or any GCM data for interpolation, just because we want to make it homogeneous for all GCM when we compare with the historical data. So we resample it, then that, and then observe here, 1, 2, cbind, that, merge it, and then if one, that, cbind, t flash. Okay, now it's extracting the GCM just now. So you see only one file here, so it only gives you only one value in the console here. Now if we run pre, this is this code just now. When we run this brick just now, we want to find the information about this GCM. So we have this GCM. Actually, the resolution is 1.25 and 0.94. So different GCM will have the original grid is different. It's not 0.25. So in this case, we do bilinear interpolation to interpolate it with our historical data. So it will be 0.25. You can do 0.5, 0.1, and whatever, and interpolate by using bilinear interpolation to that grid point that you want. But in this case, we use for 0.25 for chips rainfall data for rainfall assessment in Peninsula Malaysia. So this is the extent. This is all the information that we have about this GCM actually. You can run pre here. And then after you run the code, so you can get the information about pre. So I can put it here. Actually, it's better to be down here. Okay, run to get resolution of GCM. So this resolution of GCM, actually you can put it, for example, in your data set. not this one. Let's see for one of my uncertainty assessment just now. So this is my global climate model, right? So this is the GCM. So I can put right here. So another information for this GCM is resolution, right? So resolution for Thai ESM just now is okay. This is the resolution. You can put okay. This is let and long resolution for Thai ESM2, the original resolution before we do bilinear interpolation. So this is some more of the information that we can get when we do this analysis. We can put it into our data also to get that information. Okay, now we run this tdet run. This is the value that we will get. You know, when we run this, when we extract this GCM, actually the unit is different. It's kilogram, meter per second, something like that. So to convert it into millimeter, this is to convert it into millimeter for monthly rainfall. This is to convert to millimeter. So you times the value that you got from the original data, times it with 200, 2 million actually, 2 million 592,000 2,592,000 times with this one, and then you will get in millimeter. So and then we run this, call names, something like that, and then set the working directory where we want to extract this data. So this is the example just now. You can see here, you will get the result. See, it's very fast because monthly rainfall, it can run very fast. If you do daily data, it can take time. So we get this extract data, GCM, in for Peninsula Malaysia, 178 grid point from it's actually for the whole period, actually, the whole period of the data set. You see, if you want your data set from 1981, you can just delete the rest of it. So for my data set, if I want to compare it with CHIPS rainfall data is from 1981, so I can delete the rest of it. Oh, no, delete. So delete. Okay, for 1981, I can make it proper like this. Use data, text to column, next, other, X, and finish. And then text to column again. Next, so I like to arrange my data like this: year, month, and day. So this is your data. You see, from 1981, every month you will get the data until 2014. So this is the grid point from 178 grid point. You can refer back, this grid point is actually refer to your lat long data set just now, PM grid. So this is your lat long 178 grid point. It will be extracted based on this lat long. So that is the column heading for this extracted data. So you can see the value here is monthly data. This is all monthly data. If you can see, I can put this as V1, and then insert, you can see how the pattern of monthly data. I need to put it on the until 2024, and then okay, see, we can see pattern of monthly rainfall in Peninsula Malaysia for that grid point. So it's correct. Mostly rainfall is in monthly is about 200, 300, some extreme rainfall up to 600, 700, something like that during the monsoon season. So this is correct. So you can use this code for extracting your CHIPS rainfall data. It's not extensive. It's very simple. Not very extensive one. So I think that's all for today. Thank you for watching. I hope this tutorial will help you. If you have any question, I will not provide the code for this one because YouTube description that sometimes it cannot support some of the coding that we put down there. So just watch this YouTube read the code, try to watch it, write it your own, copy whatever, but I will not provide the code. Unless you want to do research collaboration, you can ask me, contact me, and we can do code research collaboration, and I will share you the code directly because we are collaborator after that. Okay, thank you for watching. That's all for today.